Mrs. John for Year 12 Physics, and this is the last lesson on electromagnetism. So it is quite a short topic, so I've just got 4 videos for you, and this one is on electromagnetic induction, which is also called the generator effect. So electromagnetic induction involves changing kinetic or mechanical energy into electrical energy. So in order for this to happen, we need 3 things. You need a conductor, you need something to move in a magnetic field. And explanation. So whenever a conducting wire or rod is made to move at right angles to the magnetic field, the charges in the wire experience a magnetic force, causing them to move to one end of the rod or wire, leaving the other end positive. So the charges that actually move are the electrons. Now, this charge separation causes an electric field along the wire that results in an induced voltage. The size of this induced voltage is given by V equals BVL. So there are 2 V's here, a capital V and a little v. So the capital V is your induced voltage, your B is your flux density or magnetic field strength, the little v is the speed with which you're moving the wire or the rod, and L is the length of the wire or rod in the field. Now, if the circuit is complete, there will be a current, and the size of the current can be determined if you know the size of the induced voltage and the resistance of the wires. Now, how do you find the direction of the current? Now, there's loads and loads of rules for this. There's Fleming's hand rules and your slap rules, but the way that I teach using the left-hand slap rule. Just so you don't get confused, you stick to whatever your teacher has taught you, and that is correct. Now, I just use 2 different hands. So the left-hand slap rule, it has the thumb as the direction of the current, the fingers point in the direction of the field, and the direction of the slap indicates your movement. So, and how do you know which way to point the thumb? So you point the thumb in the direction of the current, and the direction of the current is the direction in which a positive charge moves. So this is the conventional current. Okay, so here is now, if your circuit is not complete but you just have a rod, and so if you move a rod in a magnetic field and the movement of the rod is at right angles to the field, the charges in the rod will experience a magnetic force and they will move to one end, leaving the other end positive. So remember, it's only the electrons that can move. So when they go to one end, so one end has a lot of electrons, the other end is left positive. Now, this charge separation results in the formation of an electric field along the rod, and hence the charges will experience an electric force, which is in the opposite direction to the magnetic force. Because once you separate charges, the electrons will want to move towards the positive, because opposite charges attract, and that's why you have an electric force in addition to the magnetic force caused by the movement of the rod in the magnetic field. So there's actually 2 forces. Now, this charge separation continues until the electric force becomes equal to the magnetic force, or it balances the magnetic force. Now, these are some examples of a continuous loop that is made to move through a magnetic field at constant speed. So this one is a loop that's entering the wire. Now, there is a voltage induced across BC, and using your left-hand slap rule, you have your thumb pointing upwards. So if you continue that, you will have your current flowing in an anti-clockwise direction. Now, when the loop is completely in the field, there is a voltage induced across BC as well as across AD. These are in opposite directions, so they cancel each other and there is no current. When the loop is leaving the field, there will be a voltage induced across AD, and when you use your left-hand slap rule, you will get this direction, and if you continue that direction, the electrons are kind of pushed along the wire and you get a clockwise current. Now, so these are the notes on what I have just explained about the three situations. Now, the direction of force on charges. Now, if you kind of magnify a wire and these red things are all the electrons, all, no matter which part of the wire they're in, if they will all experience a force in the same direction. But along AB and DC, the charges experience a force that's kind of pushing them against the wire. It doesn't cause them to move along the wire, and that is why there is only a voltage induced across AB and BC. Okay, because these kind of just are pushed to the sides of the wire. And so here is the explanation of what I just said, and here are some questions on electromagnetic induction, which you're most welcome to take a look at. Look at my working for the first one, and then try and solve the others on your own. I've got one over here. And I think that is it for electromagnetism.